Hello, everybody. How are you doing today? Let's talk about something which nobody talks, upper air measurements. Like, why do we do it? Okay, so in this video, I'm gonna talk something about upper air measurements, and the broad agenda of my talk will be these five major points, in which the first will be why and how we do upper air measurements. Second, I will talk about the history of radio sound, constructions, its working, and then we will talk about how the variables are calculated in a radio sound and how they are actually transmitted to the ground. The fourth topic that we'll be discussing would be the uncertainty in these measurements. And the last topic that I will discuss are some specialist radio sounds or the aircrafts that are being used right now and some extra knowledge. So why do we actually measure upper air measurements? Why actually we do it? So according to me, these are the major five regions that we need to do or we need to study the upper air. The first could be about the scientific understanding of that place, like the upper air, because rainfall occurs, the clouds are there, thunder is there, even aurora borealis is there. Then even we are also sometimes there in a plane. So the second region comes to be the aviation safety. The third region is about the climate research. That why do we do it? Like why the rain is happening? Why did lightning strike? These all are there in like global warming. So we need to do some climate research over there. The fourth thing which I consider is about the weather predictions. Like why like tomorrow will be a raining day, or tomorrow will be a sunny day. Tomorrow might there be a heat stroke going on, or tomorrow might be a snowfall. So for that we need to do weather predictions. For that we need upper air measurements. And the last thing which I consider is about the atmospheric profiling. That we need to understand about the profile of our atmosphere, whether it is baroclinic, barotropic, what kind of atmosphere do we live in, right? Then, like, how do we do it, and what do we do it in that? So, a radio sound is a device which actually, as you can see in the right hand side in the bottom part, that a radio sound has been released and it goes up, and the upper is just a snapshot of that what is going up. The white spherical thing that you are seeing is the balloon. It actually varies in the mass, starting from 200 grams till 1000 grams. It depends upon the kind of measurements that we need to do and the height or altitude that we need to go. The second thing you are in red color is the parachute. That when this balloon pops, so after that this radio sound in the last thing that you're seeing, the last cubical thing, white color. So it should be dropping, or it should come to the surface of the earth slowly. For that we need to have some parachutes out there. So the red color is the parachute. Like here in the star portion, you are able to see there are five major components that a radio sound measures, and those are wind speed, wind direction, pressure, temperature, and relative humidity. Who are the manufacturers? So a radio sound maker share in the market is mainly of Vaisala. So Vaisala is the major producer of radio sounds, and it is a Finnish company. That means it is from Finland. And the second most biggest market share in radio sound making is of Meteodome. Actually, it is a UK company, UK based company, which actually makes them. But they both follow US norms, US Navy standard norms, like the National Bureau of Standards for a US Navy. Like how the radio sound technology developed. See, earlier days, kites and meteographs were used, like in the 19th century and so on. The kites were actually used, as you can see. A kite, like two or three kites, are actually flown down just to measure the upper air. So at that time, only pressure and temperature was recorded, and that too by the help of very weird devices. Like here, you can see the Dines kite meteograph. Okay, So like Dine's balloons meteograph, then actually it got further developed in 19th century. Whereas the challenges during them was the ground linkage, the maneuverability, and the transmission of the data which we actually get, as well as we were not able to explore a higher altitude area because the kite could not flow to that high altitudes. But Robert Bureau, who was the first person to invent a precise radio sound, he was actually a French guy in 1929. The term actually radio sound was coined by him only, but the Pavel Molchanov's design became much popular because they used Morse code, and we are talking here about around World War One, after World War One, something like that time. So Morse code was more used. That was the era of Morse code. But after around World War Two or so, cosmic ray reading was there because at that time physicists were much more needed because of the nuclear bomb and all. So at that time, 1935 around, um, Sergei Vernov actually adopted the radio sounds for its cosmic reading abilities, and in 1935 he actually did the high altitude reading. Okay, so mainly he was the first person to did the high altitude reading, whereas in 1936 U.S. Navy actually jumped in and developed the official radio sound. Mainly Harry Diamond actually was the project at that time and made a radio sound that was capable of measuring temperature, humidity at higher latitudes by using uh, mainly the balloon. So yeah, he did the brown groundbreaking discovery at that time. The fifth point that I am here to explain was the expansion and the recognition of this radio sound throughout the world. So this NBS style, that is National Bureau of Standards of US Navy style radio sound system, was more accurate and it was able to do automatic data collection. So everybody is lazy inside world. So it got a wider range of adoption. Hence Harry Diamond, who was the project head, received so much accolades for his contribution to the radio meteorology. Okay. So from around 1930 to 1970s, early radio sounds like Vaisala radio sound, UK Met Office designs. So these all are the UK also jumped into it. So but at that time, most of the sensors were mechanical sensors, like a Mark II, like for example, Mark II sensor. Metals were used, actually, they used aneroid capsules, which you can see in the right hand side bottom, and bimetallic strips, gold beater skin for pressure, temperature, and humidity measurements. But what was the problem that they were facing? Like, if you want to see the bimetallic strip, it's just above the aneroid capsule. So what in this happens is due to because of the change in temperature, this metallic strip was capable of actually expanding and contracting due to because of the change in temperature. So that change in temperature was recorded on a scale, hence giving the change in temperature. Similar thing happens with the Android capsule, but in gold beater skin, the humidity was measured because it actually at a higher humidity it actually expands, whereas at lower pressure, lower humidity, it's actually contracted. So what was the problem that they faced during the early design? First of all, there is so many problems. Like you are using uh, Android capsules, biometric strips. What is a gold beater skin actually? Earlier times, gold beaters used skins to actually bit their gold into very thin sheets. Okay. So the operating principle during that time main were three: the operating principles, the battery power supply, and some requirements and all. Mechanical, actually, in operating principle, if I'm gonna talk about, so the mechanical changes in sensors altered an inductor's property, modulating the audio oscillator frequency. Audio oscillation transmitted data via a long range beneath the radio sound. So it was not capable of doing such things. Okay, so you cannot go a very higher altitude. You could go a particular level of altitude. Then comes the battery power supply. Since at a very higher altitude, the temperature decreases very fast. So you need a battery that is capable of holding a very low temperature. But during that time, wet batteries were used, like alkaline or H2SO4 kind of thing. But nowadays, it is completely based to lithium type batteries, and that too low temperatures and low temperature bearable batteries. Okay, the modern radio sound sensor faces demanding conditions. Okay, measuring accurately across the wide parameters, but the challenges induced was like with the vent weight sensors in cloud and turbulence motions. Cost effective designs were essential at that time. Okay, so you need to have some cost essentials, effective as well as efficient operation, proper transmission of data that was not there at that time. So these were actually the requirements that was there. Like these were the problems at that time the radio sound technology faced. So from here actually, as you can see, the early Met 2 Met Office radio sound in the right hand side corner, it uses a special kind of technology which was called as a multiplexing, in which if more than one signal is required in a radio sound, three different signals that we require are mainly pressure, temperature, and humidity. They are actually usually sent to the radio transmitter, which actually switches in between these three sensors, and that too by using windmill. Okay, you are getting wind data as well, wind speed. So the operating principle of a radio sound that each of the mechanical pressure, temperature, humidity sensor caused a change in the inductors. Okay, so which controlled the frequency of an audio oscillator. The different inductors were switched in return to determine the audio frequency oscillator by the mechanical rotation of the windmill. So these distinct sequence audio tones were used to modulate a radio frequency oscillator, which is amplified by a transmitter stage to radiate from the antenna, and that was actually being collected after that. But the efficient battery, which was able to operate at low temperatures, were needed at that time. So M2 Mark II MO radio sound that uses the same wind vane or windmill, but after that multiplexing was discovered, and hence the multiplexing was done without the use of windmill. And furthermore, relative humidity sensors like humicaps and temperature sensors like thermistors were developed in RS80 models. It was further been improved in RS90, and nowadays there are RS92 models that are being used. So, what do you measure? It is called as a PTU measurement, pressure, temperature, and humidity measurement, in which pressure measurement are done using two different methods, either by an aneroid capsule or a hypsometer. An aneroid capsule is a method in which utilizes an aneroid capsules with temperature compensation for pressure measurements. It is a small capsule in which a small capsule movement induces capacitance or inductance variation. So it actually switches its motion on different heights. Whereas in hypsometer, it determines the pressure using boiling temperature variation in a liquid. So it offers a sensitivity at a low pressure requiring only a change of 0.5 hectopascal at the change of temperature of around 0.01 degrees Celsius. So it was simple and much more accurate as compared to aneroid capsule methods. Okay, but it simplifies the corrections without aneroid sensitivity issues. So that was also one of the plus point with this. Whereas the boiling temperature method enhances the sensitivity at a low pressure, offering an alternative like chlorophyll, chlorofluorocarbon (CFCs) or very low power hypsometer, very low power hypsometers. Like on the right hand side, you can see how a hypsometer element is used within a radio sound. Heating is provided by a small resistive heating element, and the boiling temperature determined with the thermocouple. Okay, so this is the mainly the overall pressure measurements. How are they done in a radio sound back then? But nowadays it's completely a sensor, a very small sensor of around 5 grams that is being used. How to measure temperature and humidity? So the temperature is determined using electrical sensors, such as temperature sensing beads or wires. relying on a capacitance. Actually, they also depend upon capacitance also, but here I'm gonna talk about thermistors only. So, for example, Vasala RS92 uses these sensors, and the readings are actually factory calibrated using a unique polynomial function for each device. That thing you can get from the bottom, like negative temperature coefficient method, in which if you increase the temperature, the resistance decreases. Okay, but if a positive temperature coefficient is there, so if you increase the temperature, the resistance also increases. So the negative temperature coefficient is called as a thermistor. So like here you can see there are two different components, in which a humidity sensing component and a negative temperature coefficient method of temperature sensor, which are called as thermistor. So in humidity sensor there is a change in dielectric element due to because of change in the atmospheric water vapor, and it changes the dielectric coefficient of this capacitor. Hence, by that being calibrated in a factory based condition, we are actually going to find about the humidity. So yeah, here in like Vesala 92 RS92, it employs a pair of capacitance RH sensors that alternate between measuring and heating to avoid wet bulb saturation efforts. So the time limit in between both are around 500 seconds or so. So the sensor responses are calibrated the surface in a small chamber, which is actually dried with a disinfectant. This meticulous calibration ensures the accurate atmospheric measurements during the radio sound's ascents. How do we do the wind measurements? So the early radio sound used radar tracking with metallized mesh reflectors at that time. So it achieved around 1 meter per second accuracy at 7 kilometer height. But at that time, nobody was able to go more than 7 kilometer height. The modern system actually leverages the radio navigations like LORAN, that is long range navigation, synchronously transmitting a low frequency signals for precise location determination. Whereas a GPS global positioning system satellites are now widely being available and offers is exact spatial and temporal positioning. So we don't need to do that. Okay. The radio sound receives signals from multiple GPS satellites, enabling wind speed calculations from a successive position difference with an accuracy of around plus minus 1 2 meter per second above the surface. Consideration for the GPS receiver's power uses impacts operational durations. So we need to do some considerations here as well. Here on the left hand side corner you can see it is actually a replacement. Like how can we actually replace a radio sound? Okay. So in this how actually done. Then there is like earlier time. How a radar were actually used to actually detect or track the radio sound. Since it actually used a metallized mesh reflector. So using a radar, we were actually capable of increasing its radar cross section area. Thus, we were actually able to capture from where it is coming or from where it is going. Okay, so how do we actually do the data telemetry? Okay, and how do we actually transmit that radio data? So the transducers are the things that we use, which conveys the changes in the electrical output to a radio transmitter in various ways. One method involves varying an oscillator frequency with sense parameter directly modulating the transmitter. Multiplexing also allows a sequential transmission of multiple signals through a single data channel, suitable for a slower meteorological parameter changes. So, in the modern radio science like Vaishala RS92, it uses a digital data transmission, employing analog to digital converters, and have some microcomputers are also used, like Arduino is used over there. The transmitter operating at around 400 megahertz. This is for Europe only. It generates a carrier wave through an oscillator, which actually modulation achieved by switching amplitude modulation or frequency modulation. So we can achieve that thing. The radio sound transmitters typically achieves a line of sight of range around 5 to 150 to 100 kilometers. So a radio sound transmitter can actually produce a good results for a longer line of sight. Here actually you can see a graph is being shown in which the balloon mass versus the burst height is given. So if you increase the balloon mass from 100 grams to around 1000 grams, so you can see that you are able to get a height of around 35 kilometers, whereas the ascent speed is around, you can get maybe from 4 meter per second to around 2.5 meter per second. Like on the right hand side corner, you can see a conceptual arrangement of a digital radio sound. So the measurements from the pressure, temperature, and relative humidity sensors are merged with any other measurement data. An uncommitted connection node is there. So the position data from GPS receiver by a small digital computer, and the data stream generated is passed through a modem to convert the digital signal into two different audio tones for radio transmission. So these digital tones are converted back to data at the receiver's end. The references that you can use are these.